Hello, everyone. I'm Michael from the Samsung GameDev team, and I'm here with Alexi. So today we're going to be talking about Vulkan on Android and the sort of where things are moving and how it affects performance and so on. Firstly, I'd like to thank Epic for inviting us to speak here today. And so yeah, let's get started. So as I mentioned, I'm part of the Samsung Galaxy GameDev team. We're basically a team who works with developers all around the world, supporting studios both on-site and remotely. And we're basically here to help with any problems, whether it be performance-related, optimization, bug fixing, basically exist to support the developer ecosystem and help get the most out of people's games. We're also heavily invested in promoting the use of Vulkan. We believe that this is the next generation of graphics APIs, and it's really the ultimate way of getting the maximum performance out of your games. And so today we're going to talk a bit about what Vulkan is and how you go about using it in Unreal. So why should you use Vulkan? Vulkan is an explicit graphics API. That means that the driver doesn't make any assumptions about what you're trying to do. The work is much closer to the hardware, so the commands that you issue are directly controlling how work is executed on the hardware. And this has a number of benefits. The most obvious one that's often advertised is that you have a much greater reduction in CPU overhead from the graphics API. This means more draw calls, more state changes, without having the same expensive costs that you would otherwise incur in an API such as OpenGL or older DirectX things. So this allows you to do a lot of things. It allows you to be really explicit about the work being done, which means that you can get more power out of the hardware. And it also allows you to reduce redundant work. So sometimes the driver doesn't know what you want to do, and as a result, does work that you didn't intend just because it needs to guarantee correctness. We can also reduce the amount of repeated work that we need to do. So for example, when a draw call happens, there's a certain amount of processing that would happen up front in a conventional API. We can pre-process this data, do it once up front, and then it doesn't need to be done again for the rest of the game's execution. And so basically this means that when we're working on a platform like Android, which is relatively low power, we can really squeeze out the best possible performance. So how does this work in Unreal? It's really, really simple to enable Vulkan. It's just as simple as going into the settings and searching for Vulkan and checking support Vulkan and detect Vulkan device support under the Android settings. This is the same for if you're using Windows, but I believe Vulkan is still experimental on other platforms. A few other things that you should probably be considering if you're working on mobile. So coming the 1st of August, Google Play is mandating that all apps be 64-bit. That will mean that if you're developing for mobile, it would be good to start supporting 64-bit as early as possible, just to make sure compatibility and everything is good. Again, this is really, really simple to enable. Just in settings, there is a option support ARM64, and you just need to enable that. Another thing that's worth considering is texture compression. So texture compression is a great way of both reducing your application's package size and also increasing performance by reducing bandwidth. In Vulkan, we have access to a texture format called ASTC. This is by far the best in both quality and compression ratio out of all of the compression schemes. If you also need to target OpenGLES 3, then you will need to package with ETC2 textures to guarantee support across all platforms, as ASTC is not supported everywhere. If you're targeting an older version of OpenGL for backwards compatibility, then ETC1 will also be needed. But if you're just using Vulkan, which is what we're kind of strongly recommending, then ASTC is the way to go forward. And this is just something, again, that you can find in the project settings. Finally, just a note on the Android SDK. This option basically controls what systems, what phones the application can be installed in. This is somewhat arbitrary and kind of depends on what you're targeting. So in this case, we've set minimum SDK version to 19. This is a slightly older version, but if you're targeting both GL and Vulkan, that's the sort of thing that you probably set your install threshold to. Vulkan became available in Android 7, so if you're only targeting Vulkan, then the SDK version needs to be high enough such that you don't target below 7. Otherwise, the devices just won't be able to run the game. And finally, regarding NDK settings, this is a question that we get a fair bit. What do we set it to? I'd recommend just setting it to the latest. And this will mean that you've got the most up-to-date version of the build tools being used to compile your project. Finally, again, because it's useful to support both Vulkan and OpenGL at the moment, you probably want a way of being able to switch between the two. This is really good for being able to just easily compare performance between the two APIs, so that when you enable Vulkan, you can actually measure what sort of performance difference you are getting. And there are two easy ways of doing this. The first is to modify a console variable in the device profile, and r.android.disable Vulkan support will ensure that the Vulkan API does not get used for that specific device profile. This again is mostly used for device compatibility if you know that you're targeting some devices that don't support Vulkan. But it can also be used to create an OpenGL version, profile version of your title if you need to test that. The second thing is a more dynamic thing. We can actually modify this Android environment variable, debug.vulkan.layers. This is also used to control validation layers, which Alexei will go into more detail about later. If you set this option to vk-layer-gl, then this will ensure that OpenGL is used when your application is launched. And this needs to be set when the game isn't running. So say you've plugged in your device to the computer, you type this command into your console, and that will allow you to toggle between Vulkan and OpenGL. But moving on to something more interesting, where is the Vulkan ecosystem at? So Vulkan's a relatively new API. It hasn't been around too long. So currently, as far as Samsung goes, we have quite limited device coverage. We support the full range of the high-end stuff from the S7 onwards. So that's kind of S7, S8, S9, S10, and all of the variants there and in between. And then also the Note 8 and Note 9. In the future, it'll be really cool because we're going to be supporting Vulkan across the entire range of devices. And this is going to be really significant because the main benefit of Vulkan is that saving in CPU overhead. And this becomes really relevant on the lower powered and lower end devices. Finally, I'm sort of going to talk about some really useful Vulkan-only features. So because the API is new, we have a whole host of features that are unique to Vulkan that you just don't have access to if you're using another API. And I want to also discuss some of the tools that we use. And these are the kind of tools that you can use in your development process to really get the most out of your game, and just to make sure that you're running at the highest possible frame rate. So first tool is RenderDoc. And this is basically a high-featured frame debugger. We find that it's really, really good when using Vulkan. It gives you really detailed breakdown of all of your API calls, and it also allows you to visually verify exactly what is happening, so you can step through a frame call by call and work out how that frame is composed. So in this case, we're looking at the UE4 Sun Temple demo on mobile, and this allows us to kind of debug frame by frame and really look at what's going on and how that work is being executed by the GPU. This gives us a lot of control. We can identify both engine level optimizations that we can make, such as optimizing render passes, which I'll go into more detail later, and content side optimization. So for example, if we see a draw call that is being rendered but isn't really on screen, or if something's being drawn and then something's being drawn over the top of it, so in an overdraw situation, this is also something that we can find with this tool. And again, it kind of allows you to make informed content optimizations that can be really useful. The other main tool that we use are kind of static counter-based profilers. The top one is called Streamline, and that is used primarily for ARMS hardware. So the Samsung phones ship with two chipset variants, ARM Mali and Qualcomm Adreno. We use different tools depending on which device we're testing. So for ARM stuff, we can use Streamline, and this gives us a really, really high-frequency breakdown of exactly what the hardware is doing. So we get information about fragment activity, detailed CPU breakdown by core, and sort of vertex activity and things like that as well. We can also zoom in at a really high resolution on that data. So kind of looking at this bottom chart, we can see exactly how the fragment and vertex work is being executed. And this would just be kind of a breakdown of areas within a frame. In this case, we can see that there are quite big gaps in the middle of our trace, and that basically implies that the GPU is being underutilized. And this is something that's really, really hard to find unless you're using these specific tools that can give you access to that information. So, Vulkan features. These are the kind of three of the current features that I want to talk about today that are in Vulkan and can give you an immediate benefit in Unreal. And for all of these, you pretty much get them for free straight out the box just by enabling Vulkan. And then in the future, there are some other features coming to future versions of Vulkan that will also be really relevant for game developers. So the first one, present timings. This is a new extension that was initially created by Google. Frame pacing is used to sort out the issue of frame instability. Sometimes with games, you have a huge variance in your FPS. One frame could take 10 milliseconds to render, the next one could take 30. And this can all be down to like how much content there is on screen. If you've got a high amount of dynamic content that comes and goes, especially in open world games, you can find that as you walk into a new area, you get stuttering and all sorts of just crazy variations in performance. And what this means is the game experience isn't really smooth and it doesn't really reflect the artistic intention of the game. So frame pacing it becomes really important. And this extension allows you to kind of smooth out your frame rate by setting certain properties and timing information for those frames. So in this case, you can just enable this extension again with a simple console variable, and Unreal will handle the rest. And what this results in is, if we start with a trace like this, this is kind of a representative normal game that we might get, and we can see that the frame times are very variable. This kind of blue indication here shows us the total frame time. And it's very up and down, very spiky. And this means that when you're playing the game, it's just stuttering all over the place. And it's not a very nice experience. It becomes frustrating to play. By enabling this extension, we can completely get rid of that. So what we have here is we're basically introducing a minimum bound. So we're saying that a frame will be displayed for at least a certain period of time. And this will depend on the target frame rate of the game. But in this case, it's around 33 milliseconds. And what this means is we get a much smoother experience. Because the variance between the minimum and maximum frame rate is minimized. And so this, if anything, will reduce your FPS slightly, but it will give you a much smoother experience. And that's more important in many cases than having a frame rate that can go high or run at a high average, but has very different highs and lows. So another feature that's kind of cool is pipeline caching. So when you're doing a rendering work, there's a load of state that needs to be calculated sort of to determine what's going to be rendered. So this includes kind of shader compilation on the hardware and all of the properties that go into defining how something will be rendered. So culling options and draw distances, things like that. The problem with this is in a very dynamic engine like Unreal, you have lots and lots of variable state that's constantly changing. And this means that if you say if you walk into a new area and you suddenly start using a material that hasn't been used before, all of this state needs to be prepared and created. This is also done at load time quite a lot, and preparing this state is expensive. So in Vulkan, we've got a pipeline cache, and what this means is that all of that information, once it's been calculated and processed once, it gets stored and also gets saved back onto the disk. So on subsequent runs of the game, we are potentially getting a significant reduction in hitching and a reduction in loading times, which is really beneficial. The only note here is that the pipeline cache, because it does get saved out, it can get quite large. There should be options to control the maximum size of it, but ideally you want to be able to try and pre-cache as much information as front as you can. If we have a look at the kind of performance changes that you can expect with loading, we can see here that in the bottom case, we're going down from a 5.5 second loading time for a given level down to 0.2 seconds. And something like this is just really significant. And that's just because we no longer need to pre-process this data every single time we run the game. And this is something that, say, a conventional API like OpenGL, because the driver can't make assumptions about what you're doing, and it's kind of this abstract global state that you're working with, the API cannot know some of these things up front, so it can't necessarily make those assumptions and cache that information in the same way that you can in Vulkan. So again, the end result of this is that you get less hitching at runtime, which means a smoother gaming experience, and the player doesn't have to sit around waiting for things to happen. The final feature I want to talk about is a pretty big one. This is something that's newly coming to Unreal in future versions, and it's subpasses. So in Vulkan, we have control over many more aspects of the rendering pipeline. Conventionally, we organize our work into render passes, but Vulkan also offers this thing called subpasses, which are small routines within render passes, which allow us to better coordinate our work. This is really important for mobile architecture because mobile architectures use a tile-based rendering system, which means a small subsection of the screen gets rendered at any given time. What this means is that, say if we've got something like a main render pass followed by a translucency pass, conventionally, because that translucency pass is often dependent on the scene information generated in the first pass, we need to complete the entire first pass first, write that data back to main memory, then move on to the second pass where we can consume that data. What this means is that you kind of have this unnecessary writing back of information, whereas on a tiler, we have the benefit of working on tile, keeping that memory in the local cache, and moving straight onto the next pass for that given workload. So in this case, we can do the transparency pass on tile straight after doing the previous pass without having to write any data back to main memory. This results in a pretty significant saving in bandwidth and a proportional saving in both power and performance. So to go through some cases of where this is possible, this is only possible if your materials and shaders are sampling the same local value in your frame buffer that was written to in a previous pass. So the most common thing here is if you're rendering some sort of effect like water or God rays, these often do some sort of depth sample in order to do a smooth fade. And these shaders will sample something like the pixel depth node. You might have this in your material. And this is a perfect case for subpasses. We know that after we've rendered the main scene, that information is immediately available. And it gives us the benefit that we can collapse a secondary render pass down to be a secondary subpass of a previous render pass because we're using exactly the same input information as was just written to in a previous pass. Unfortunately, this isn't possible if we need to do sparse sampling. So for effects like blurring, these require sampling lots and lots of pixels around. Because the values that we need to sample may not be on tile, we can't actually make use of subpasses in those cases, and then we do need to fall back to writing out the tile data back to main memory. But for the translucency pass, which is probably the biggest use case that we come across when working with projects, this is definitely something that can be optimized, and there are a number of other things you can do as well. So if you have secondary passes that are dependent on data generated in a previous pass, then this can be done. This is also useful for, say, deferred lighting, because you can render your deferred lights in a later pass, and again, save having to write all of that data back to main memory, especially if you've got quite a heavy GBuff where you've got depth data, normal data, other material data. This is a huge saving. So another thing, so when you're trying to work out whether this is possible or not, whether you can make this optimization, sometimes we don't know. Sometimes we only have access to kind of the final end result shader. And the easiest way we can do this, say if we've just got a shader that does some arbitrary sample on some texture or input attachment, then we can do this basic comparison just to compare the local on-screen coordinate that's being tested against the value that we're sampling from some texture. In this case, the output from these God rays up here was rendered as white. And we're using RenderDoc, which was the tool I talked about earlier, to do this shader analysis. So in this case, we can determine that actually, yes, even though we've got this thing that looks like a sparse texture sample, it does turn out that it is only sampling the local pixel coordinate, which means that that data will be available in on-tile memory. So we don't actually have to do a texture lookup for this. We can instead load the data immediately from the Subpass data and get that performance saving. So in this case, again, we've verified that this pass is compatible with subpasses. And when we apply the optimization, we can get something that looks a bit like this. So this is the standard trace with the default Unreal render in the Sun Temple demo, where depth, color, and stencil information are stored between render passes. Currently, we have this big block here of this kind of time that the GPU spends idle. This is the time when that data is being written back to the GPU, from the GPU to the main memory. And this is unideal. We're basically just wasting a millisecond doing something that we could completely avoid doing. And so when we enable a subpass optimization, and again, this will be something that's very easy to do in Unreal once the features come out, we end up getting a significant reduction in GPU idle time. So now we've gone down from the total idle time of the GPU in the frame being 1 millisecond to being 0.15 milliseconds. And along with that comes a measurable bandwidth saving of 700 megabytes. What this results in is a 6% performance increase, which doesn't sound like much, but bear in mind we're doing exactly the same amount of render work. So this is essentially a free 6%. In terms of FPS, we got from 52 to 55 FPS. The only other thing you may question is why is the CPU usage now higher? The reason for that is because we're now processing more frames, and because those frames also require a certain amount of CPU work for your physics simulation or whatever else it might be, then that also goes up. So, looking at kind of upcoming Vulkan features, depth stencil resolve. So, for those who don't know, resolving is when you take a MSAA buffer, say something that you're rendering with anti-aliasing and multi-sampling, and you collapse that down into a normal resolution non-MSAA buffer. This is normally done at the end of the frame, so you render your scene with MSAA, and then you collapse it down, which is the process of averaging the values of the multi-sample pixels, and that's what ends up giving you the smooth edges on geometry. Currently, MSAA is really, really cheap on mobile. Again, it's one of the benefits of having a tile-based architecture. Multi-sampling can be done and resolved on tile. And this means that we never have to write that MSAA buffer back to main memory, so we get a huge bandwidth saving, and the actual increased sample rate doesn't really affect performance significantly. One problem with this, though, is that up until now, it hasn't been possible to resolve depth, at least not efficiently. So there's a new extension in Vulkan coming, which also allows the efficient resolving of depth on tile. And currently, certain post-process effects, which depend on using the depth, haven't been possible. Say, like depth of field is an example of a post-process effect that just isn't possible efficiently if MSAA is enabled on mobile. Currently now, though, with this feature coming, this will be possible, and it means that we'll be able to enable MSAA on mobile at a very, very low performance impact, and also benefit from maintaining performance on secondary passes which need to use that resolved MSAA buffer. Again, this is something that the engine will be able to do completely for free. You won't have to worry about it, but it's just cool to be aware that this feature exists, and again, is only available if you're using Vulkan. And this is another example of something that can both allow you to benefit from performance increases and also benefit from a increase in quality for your projects. So yeah, what's the future of the Vulkan ecosystem? I mean, as I mentioned earlier, we're going to have better device coverage across the whole range, which means that both the low-end and mid-range devices are going to be supporting Vulkan. In my opinion, this is going to be really significant because those are the devices that need the most optimization and the ones that suffer the most from CPU bottlenecks. And so what I'm suggesting is that you start using Vulkan today, give it a go, see if it benefits your project, and basically prepare yourself for the future. So I'm going to hand over to Alexi now, who's going to go through some case studies of projects we've worked in and some more practical usage examples for Vulkan. Thank you.
Thank you, Michael. Hello, everyone. I'm Alexi from Galaxy GameDev team, and I'm pretty sure everyone here heard about Fortnite. So last fall, it was finally released on Android with Vulkan render enabled on some mobile devices. So here is the video from Galaxy Note 9 device. And as you can see, performance boost with Vulkan is quite huge. So actually 20% in average or something like that. Actually, game dev engineers and Epic Games engineers together work really hard about improving Vulkan render stability and performance. I will not dive deep today about what features were added during that collaboration or what optimizations were done. If you want to find out more details about that, you can just check out our GDC talk about bringing Fortnite on mobile, or you can catch us later in our meeting room. We will really happy to ask at all your questions. So the key point about all of this is that all these features are finally included in the Unreal Engine. Starting from 4.21, Vulkan build stopped being experimental on mobile, and now you can run your game with up to 20% faster on Android with Vulkan. And this is really cool. As Michael shown, you just need to make a few clicks and that's it. Here you go. You have your benefits. But how to be if you already started to develop your game but still want to use Vulkan? So I believe you have a few options. So probably the most obvious way is simply to update your engine to the latest version, but it may be hard to do because you already might customize your engine, you might add some specific features which will be hard to port, or maybe you're using some third-party libraries that are already deprecated and not used. So that's why probably the better will be to use second solution, which is backporting. So you can just backport the latest Vulkan RHI to your current engine version. Even it is quite complicated and you may make some mistakes during porting, it still may require less efforts from engineers to do this compared to the first solution. And there is always third way, you can contact with us and we will do our best for you, as we already did for many game developers all over the world. So anyway, if you decide to go by your own, here are some practical advices for you. So after you finally got your stable Vulkan renderer, probably the first thing you should pay attention on is load and store operations. RenderDoc is very useful for that. So here you can see some load and store operation captured. So in the new APIs like Vulkan, you can explicitly say what memory transfers will happen with your attachment. This was quite implicit in OpenGL, but yeah, in Vulkan this is like absolutely explicit. Since the memory transfers are very important, the onus is on you to get this right. So, and actually it is very easy to left some transfers accidentally while you are porting your game. For load operations, if you will write over the whole attachment, for example, like color frame buffer, probably the most efficient, the best thing you can do is to say that you don't care what was in that attachment before. And still, clear is also quite efficient on tiled GPUs, so you may use that as well. For store operations, if you need to preserve the previous render target, you definitely can do this, but don't do that unless you really need to, because transfers from frame buffer transfers to system memory are very expensive. Similarly, only write out attachments that you want to keep. Don't preserve depth or multi-sampled buffers if you don't really need them. In Vulkan, you should always reuse all your resources. You should always try to reuse all your resources as much as possible. Especially updating descriptor sets is very performance expensive. So it's always better to have some kind of descriptor set cache logic in your game. In that case, you have to calculate some hash values for your resources. From the first look, it seems like it is fine to use some resource info like ranges of offsets with handle value which points to Vulkan resource, which might be image, buffer, sampler, whatever. But according to the Vulkan spec, there are just few lines about that, so it is really easy to miss that. Handle values may not be unique within resource type or across different types. So you may have some unexpected hash collisions, which are very annoying to fix. So the better way is just to implement your own ID generator and to use your own unique IDs to make sure everything works right. Render passes. So beginning and ending render passes, like most operations, have some cost associated with it. So you should never have kind of empty render passes like this without any draw calls, or that are not really needed like this. In UE4, you may break render pass every time set render target function is called. So we noticed several problems from our gaming experience. So first problem was with some UI logic. This one. So as you can see, each UI icon was rendered in separated render path, and it was redrawn every frame. So at some frames we got kind of 70 render passes, which is kind of ridiculous value. It's really huge. This problem might only be fixed on the application side, so please organize and manage your UI properly. The second problem was that some render passes don't have any draw calls, but still they were called. So for fixing this, we added some logic called pending render pass. With that logic, beginning of render pass was delayed till the actual draw call happened. From PC experience, you may know that uploading buffer data happens through staging buffer because you have to transfer your data from system memory to video memory. So it usually goes like this. So you are copying your raw data to staging buffer with CPU access. Later, you are recording some copy command, and after proceeding this command, you finally get your data on GPU. But on mobile, we have unified memory access, so this is a necessary step. You can just directly copy your data to GPU, and you can skip double copying in such situation. But for images, this is still might be requiring, and here is why. So there are two ways of storing images in the Vulkan. First one is linear tiling. With it, the textiles of your image are laid out in memory in the raw major order, and this order in which the order in which pixels in triangle are processed is unlikely to suit that linear tiling order if we're talking about some triangles that has arbitrary orientation. That is not good for, that might not good fit to GPU cache. So in this case, optimal tiling is a better way to go because with it you will have a better locality of reference when accessing the texture. But tiling optimal algorithm is proprietary to each GPU, in part because it depends on some cache size and some internal details of memory controller. So we don't know exactly how data is stored there. Still, you need linear tiling for CPU access, and if your image is updated every frame, it is better to use linear tiling as you can skip extra copying. But if you are not doing this, tiling optimal is usually more friendly to GPU, so it's better to go with it. There is another concept in Vulkan called layout, which is quite similar to tiling, but I mean, it sounds similar, but this is quite different thing. So it's intended to be more specific about how images will be used in order to let hardware to use techniques, some specific techniques like frame buffer compression or hierarchical Z. So it's the best to use the most specific layout that is appropriate. Even you might see any benefits on your current test hardware, maybe newer hardware or newer drivers will use it. So here are some most common layout transitions. When you just create your image, it is in undefined layout, and there are two ways to use it. So if it's just like shader texture, you need to upload data to it first. At that moment, you should specify transfer destination layout, and then after setting shader read-only layout, you can use your image as texture in shader. Second way of usage is using like render target. In that case, you need to set your image to color attachment output layout, and before drawing something. Yeah. And maybe later you will decide to use this render target as input texture for some post-processing or environment mapping, so you should transit it to shader read-only layout. And if this is image, if this is swap chain image that will be later presented on screen, you should set it to present source layout before actually presenting it. And for each such transition, you must to use specific pipeline barriers, as you have to make sure that all work with the image in previous layout was done before starting to use new layout, as it may cause some flickering issues or some performance degradation stuff. The good thing is that even you miss some layout transition, even you miss some barrier, you can easily find that by using validation layers. Actually, validation layers will report you everything what you are doing not according to Vulkan spec. It is very easy to enable them in Unreal Engine just by setting properly these console variables. And the difference between them is just which layer will be called. That is the difference. So fixing all validation errors is the key to get stable Vulkan renderers. So you should do this first before you make some performance optimizations. Let's talk about performance budget on mobile, as it is quite limited, so we should care about it. So there are 3 possible cases. First one is CPU bounding case, second one is normal case, and which is like the best one, and third one is just GPU bounding case. As we mentioned earlier, Vulkan has really low CPU overhead, so it is very useful for reducing CPU load in first and second cases, but unfortunately, still there is not much we can do when we are GPU bounding. As Michael mentioned earlier, there are some specific things like subpasses, but they might be useful only in some specific cases. So generally, you should to deal somehow with your game content and game quality settings in this case. And as game development is always kind of trade-off between performance and quality, first of all, you should understand your performance target. So assume we have our game running in HD resolution with 30 FPS. If we increase resolution to Full HD, we will get about twice higher GPU load. And targeting 60 FPS and Full HD will affect both CPU and GPU, and will increase CPU load about twice, and GPU load will be 4 times higher compared to initial scenario. So writing some good shaders, some clean shaders, is a really good way, another good way to reduce GPU load. So while optimizing games, we often face a situation when some shaders use discards, even that might be avoided. So discard usage will stop early depth test algorithm execution. So in that case, your fragments will be overdrawn many times, and that will cause GPU load increasing. So you should keep in mind that every time you are writing something in fragment shader to your depth buffer, your early depth test algorithm will stop executing to preserve depth correctness. Here are some numbers. So after removing discards from shader, we got kind of from 9 to 20 FPS boost based on devices and different quality settings. Also, Unreal Engine has a variety of ways to set up your quality settings. So first one is scalability groups. With them, you can pack all related settings together and use them as just single number in your game for each quality level. And this group may include resolution, LOD distance, textures, quality, shadows, and so on. So you can design that per platform, and you can define some console variables to change that even in runtime. And another way to set up quality is to use device profiles. With device profile selector, you can specify quality settings per your device model, or even per GPU model, or even for your baseband version. So you can specify the precise quality you need for each device. And so you should keep in mind that device profile will override scalability groups and will override default settings, so be careful with that. Finally, I want to introduce a new performance tool from Samsung, which called GPU Watch. It is the good thing about it that starting from Android P, it will be a part of your settings, so you can just go to developer options and turn on GPU Watch, set up application you want to watch, and select rendering API that application will use. And that's it. You can start to profile your game. So you don't need any root permissions, you don't need any installation stuff or any PC connections, and you can still get your result directly on screen. Here, how it looks like. So on the top left corner, there is some FPS info. There is current FPS and average FPS among last 100 frames. On the top right, there are CPU, GPU related counters. On the left, there is screenshot of the frame captured by GPU Watch. Periodically, GPU Watch will recapture that frame. And on the bottom, there is all GPU profiling information about that captured frame. So you can easily see, for example, like all render passes related info. The first number is this one. First number is the render pass number. Second one is the draw call count, and the third one is the payload. So with this information, you can easily, for example, remove all unnecessary or empty render passes. And here is some GPU activity information regarding vertex and fragment jobs. So here you can see we're quite busy with fragment jobs. So probably you can improve your performance by fixing your shader side. So this is it from me today. Thank you for listening, and I really hope you will try to enable your games, Vulkan in your games. So feel free to ask any questions, and if you want to talk more in details, you can go and talk with us in meeting rooms. Thank you.